Hey physics students, 2015 number 1 free response question. What we got here, like we did something like this in the lab at some point. We got a ramp here, and we got some kind of cart block type of thing that we're going to project up the ramp, and there's a motion sensor here at the top. They have it set up, if you read carefully, that down the ramp, that this is the positive direction. That's important for lots of parts here to understand that. And it's projected up the ramp with an initial velocity v sub 0. And this is this angle is theta. Let's see. Is there anything else? Oh, and this initial position here, from here to here, where it starts at, that length is d, capital D. That's its initial position, like it's x sub 0. All right, let's see what we need to do here. Consider the motion of the block at some time t after it's been projected up the ramp. Express your answers in terms of md, v sub 0, t, and theta, and physical constants like g as appropriate. So A1, they want us to determine the acceleration of the block. You could make a force diagram here. It's possible that you might just feel like you know what the acceleration of the block is because it's frictionless and it's on a ramp, so I think we know what that is, maybe. But you could also make a force diagram if you wanted to. The force of gravity would be mg. Since it's on a ramp, would break that up into its components. And the normal force would be equal to that. That would be mg cosine theta. And then this would be mg sine theta. So the net force on the block would just be this, right? Those balance out, so we just have mg sine theta equals ma. So the acceleration of the block is g sine theta. If there's no friction, this is always the case, right? It's the sine component of gravity. It's worth pausing here to make sure that we've got the right sign on this. The direction of the acceleration would be down the ramp here, and down the ramp is the positive direction. So it's actually going, that initial velocity is up the ramp, that initial velocity is negative. So be careful about that, parts coming. So there's our answer for part A. A1. A2. Determine an expression for the velocity. So velocity, you can pull the equation off of your formula sheet if you don't remember it. Velocity is equal to at plus vi. So the velocity here at time t is the acceleration, g sine theta, times time, plus the initial velocity, but the initial velocity here is in the negative direction, so I would have to make that minus v sub 0. Right, so this is all kinematic stuff. Determine an expression for the position of the x of the block. So again, I know that position as a function of time is equal to 1/2 at squared plus vit plus the initial position. That's on our formula sheet as well. So here, that's 1/2 times g sine theta times t squared, and then the initial velocity is minus v sub 0 t, and the initial position is, well, it starts at this distance d from here, so the initial position would be d, And they gave that as a distance, so we should think again about the sign of that, if that's right, the SIGN. This is the positive direction, so its initial position would be positive. So there's that. Leave you that for just a second. Look at it. You could also get that by just finding antiderivatives and making sure that you solve for the correct plus c, but we know these kinematics equations, so either way it would be fine. Part B, derive an expression for the position x min of the block. Well, the minimum position, since this is the negative direction, the minimum position, like the smallest position it will have, since this is the positive direction, is when it's up here at the top of the ramp. So that's when the velocity is equal to 0, right? That's happens at the turnaround point. So what's the time when the velocity is equal to 0? Well, we have this. So velocity is equal to 0. So the time here, solving for t, would be equal to v sub 0 over g sine theta. And then plugging that in here would give us the position. So the minimum position happens at this time. So that's 1/2 g, well, I keep writing gin, sorry, g sine theta times t squared minus v sub 0 times t, again, stop doing that, plus d. That does simplify, and there's another way to get this, excuse me, using a kinematics equation. But you could certainly leave it like that. I'm going to go ahead and simplify it just so you can see how it matches up to what they have in the scoring guide. But that is correct, and you could certainly leave it like that. So very carefully here, let's see, I've got a g sine theta squared here. So I've got, we'll leave that 1/2 on the outside there. And then I've got one of the g sine thetas, the one that didn't cancel. And then I've got a v sub 0 squared minus v sub 0 squared over g sine theta. You can see that those have pretty much the same denominator, plus d. So I've got 1/2 of one of these minus a whole one of these, so that's minus 1/2 of one of those. So that's the simplified version of that. All right. Let's see what we need to do next. Some kinematics graphs, kinematics curves. I'll do those up here. So C, we want an x versus t graph. Now, it starts at a positive position, and it moves in the negative direction, never gets to 0, and then comes back again. And this is constant acceleration, so I know this is going to be some kind of parabola. So, moves like this. And if you have that right, you can think calculus like, so here, what's the slope of this? It's some negative number. The slope here is 0, and the slope here is positive. You could also get that graph by thinking about, well, its initial speed here is minus v sub 0, and it has a positive acceleration. So that works too. And then here, its acceleration is just positive g sine theta. That's those. And part D. After the block slides back down and leaves the bottom of the ramp, it slides on a horizontal surface with a coefficient of friction given by mu sub k. They want an expression for the distance the block slides before stopping. You could do this using work in kinetic energy, or you can just do kinematics. Since we're in kinematics mode, I think I will do that. So the sum of all forces once it reaches the bottom of the ramp, we're going to have a negative frictional force, and that's it, right? It'll just the force diagram. Don't need to make one, but if you wanted to, no ramp anymore, so just mg, normal force would be equal to that, and then there's our friction force. So mass times acceleration is equal to frictional force is mu, and they call that mu k, so I'm going to respect that, times the normal force, which is just mg. And now I want to know what the distance is before it stops. So that's a kinematics problem where the initial velocity is v sub 0. Since there was no friction, it'll have that same speed at the bottom of the ramp. And the final velocity, we want to know how far it goes when it comes to a stop. And then delta x, that's what I'm looking for. And I know the acceleration is negative mu sub k times g. So the distance, it's this equation again. Delta x is equal to 1/2 at squared plus vit. And I'm looking for that delta x here. The delta, it's from 0. They just want to know how far does it go. So I'm just solving for this. I don't need an initial, the initial position is 0. So that's 1/2 a t, ooh, whoops. Just kidding, it's not this kinematics equation because we don't have any time involved here. So let's scratch that. It's the Vf squared equals Vi squared plus 2a delta x. It's that one. Sorry about that. So this is 0, so it's getting a little crowded here. Vi squared, right, it's my Vi, minus 2 mu k g delta x, and I'm solving for delta x. So delta x is equal to the v sub 0 squared over 2 mu k g. And again, there's more than one way to get that. You can do that with work in kinetic energy. You can check out the scoring guide for that alternate solution for that. And one last thing, try to squeeze it up in this corner so I don't use another piece of paper. Part E, they want to know now if there's friction on the ramp, then what would the velocity versus time graph look like? Well, what's going on then? If there's friction, then just refer back to the force diagram here. Friction always opposes the direction of motion. So when it's going up the ramp, you're going to have mg sine theta down the ramp and friction this way. So that's going to give it a greater, the magnitude of the acceleration will be greater because I'll have more net force in that direction. Now, after it gets to the top of the ramp and turns around, the friction will oppose the direction of motion, and then the net force will be this minus the friction force. So I have two different accelerations, a greater magnitude on the way up, which will mean steeper, and less magnitude because friction's opposing this on the way down. So let's see, are we going in a positive or negative direction at the beginning? At the beginning, I'm going in a negative direction. So I'll start here, negative, and it's going to be steeper here because mg sine theta and the force of friction are the same direction. That means the magnitude of the acceleration is greater. So that's a steeper part, and then less steep after that. The slope of this, the slopes of these two pieces are the accelerations. Right, so here it's going to have friction conspiring to make it a greater magnitude acceleration, and here friction is conspiring to make it a less acceleration. All right, good kinematic stuff. Pretty much we could have done that entire problem back at the end of, geez, I think we could have done that in chapter 2. Right? All kinematics and kinematics graphs.